everyone, welcome to our lesson today. It is our last lesson of chapter 7. From here on out, we will just do some reviews and eventually have our test over chapter 7. If you remember, chapter 7 is all about exponents. So we started off with kind of the basic exponents with the MA, the DS, and the PM. And then we went to scientific notation. And yesterday we talked about exponents that were fractions or rational exponents and how it related to radicals. And so today's the last day. We're going to talk about what exponential functions look like when we graph them. And these are more real life. So there are a few cases in real life that they either grow exponentially or they decay exponentially. And you might have actually heard people talk about that before and never known what it meant. So we're going to kind of discuss that today. There are two main things that we are going to learn by the end of the lesson. So the first thing is that you can graph exponential functions. So knowing what a graph of an exponential function looks like. And the second thing is knowing the difference between exponential functions and linear functions. We've already learned what a linear function looks like, but now we're going to talk about the difference between the two. Okay, so hopefully by the end of the lesson, we will have covered both of those things. Okay, so I'm going to start off with, this was one of my favorite movies when I was a kid. So if you've ever seen the movie Gremlins, that's what I'm referring to. So Gremlins is like this little creature that starts off sweet and innocent, and if you got it wet, it started to multiply, and if they would eat after midnight, they started like getting evil. And so that's what this question was based upon. So Emmett, Mrs. Beckman, so my son, wanted a pet. He decided that a gremlin named Gizmo would be the perfect pet. At the beginning, night 0, Emmett did really well taking care of his pet. However, on the first night, Emmett got Gizmo wet. That happens. He's only 4 years old. So Gizmo then split into 2 gremlins. So instead of 1 gremlin, I now have 2. Then on the second night, Emmett put both gremlins in the bathtub and they both split. So now there are a total of 4 gremlins. All right, there are 3 things that I would like for you to try on your own, and then we can discuss it together. One, I'd like for you to make a table showing the amount of gremlins that will be at the Beckman house. Why? If Emmett keeps this up each day. So for example, on day 0, we started with just 1 gremlin. After 1 day, that gremlin split, and so now I have 2 gremlins. And those 2 gremlins split, so on day 2, it said there were 4 gremlins. So keep going with that table. So that is what you're supposed to do in number 1. In number 2, figure out how many gremlins there would be after 10 days. And the third one, the challenging one, is to write a function rule. So you guys are used to writing linear functions like y equals 3x plus 2. And that represents linear functions. Now we've already talked about how these aren't linear functions. They're not going to look like that. We talked about in the title that it's going to be an exponential function. So it's going to have an exponent in it. That's your hint for the third one, is to write a function rule for the table. All right, so go ahead and pause the screen now and see if you can continue to fill out that table. Find out how many gremlins there will be if my son keeps doing this after 10 days. And then see if you can write the function. All right, go ahead and pause now. All right, here's what you should have gotten. I already have our table filled in. So each time it doubles. So if you notice, 1 went to 2, we multiplied by 2. 2 went to 4, we multiplied by 2 again, and multiplied by 2 again. And if I continue that pattern, this is what the table should have looked like. And on day 10, following that pattern, I would have ended up with 1,024 gremlins if my son did the same thing for 10 days. We definitely would be going crazy at our household if that was the case. Okay, now the harder part is writing the function rule. And so the rule is it's always going to be still y equals. You guys are used to that. And to figure out what the rule is, we take what it's multiplying. So in this case, it's multiplying by 2. So I'm going to put 2 as my base. And then x is my exponent. So anything to the 0 power, if I would plug that in there, 2 to the 0 power would be 1. 2 to the first power would be 2. 2 to the second power would be 4. 2 to the third power would be 8. So our exponential function for this graph is 2 to the x power. Okay, so those were the 3 parts, or the 3 questions I asked you to do. I also want you to see what this graph looks like, because it doesn't look like a line. Okay, so when graphing, I'm going to just kind of put in my points. 0, 1, so that means up 1. 1, 2 would be right 1, up 2. 2, 4, so right 2, up 4. Then we have 3, 8. And then we would have 4, 16, which is already going to go off my graph. And so our graph starts low, and it kind of curves on up there and goes high. And that's what this graph should look like. And you might have heard of the term when people say like something grows exponentially, it's skyrocketing. It just keeps going higher and higher at a very quick rate, especially at the end, especially if it's doubling each time. Okay, so that's what an exponential function looks like. It's going to have one curve to it. It's, if you remember when we graphed like x squareds, that was a U-shaped graph. This is like, it doesn't have the other side of the U. And actually, if this graph would go on forever, it would never go under 0. And I'll show you why here in just a little bit, why it would never go under 0. Okay, so this is called exponential growth. And you can recognize it in a table because the x value is going to be increasing by a constant number. So if you notice on our table, the x's were going up by 1. However, the y value is multiplying by a constant number. So in linear functions, we'll be adding a constant number, but in exponential growth, we are multiplying by a constant number. So that's what makes it exponential growth. All right, so let's try another one here. We have a Jurassic Park example. In college, Mr. Baird figured out a way to make Jurassic Park actually be possible. He started with 160 different dinosaurs. So if it says started, that is at 0. So at 0, 160 would be our starting point here. It said, but Mr. Baird ran into trouble. After just 1 month, he only had 80 dinosaurs left. So again, after 1 month, he had 80 dinosaurs left. So that's our next point. After 2 months, he lost half of those 80. So at 2 months, he lost half. So figure out what that would be there. And question 1 says to go ahead and create a table to show how many dinosaurs Y Mr. Baird had after X months. So finish that table. So question number 2 is when will Mr. Baird have only 5 dinosaurs left? And question 3, see if you can write a function. Again, it's going to have an exponent in it. So see if you can write a function that represents what is happening in this problem. All right, go ahead and pause the screen now and see if you can do those things. All right, let's see how you did here. This is what your table should have looked like. We should have had 0, 161, 80, 240, 320, 410, 5, 5, and 6, 2.5, or 5 over 2 if you wrote it as a fraction, and you could even gone farther. 7 would have been 1.25 or 5 over 4. And notice each time our table was dividing by 2. Okay, so that was the answer to question 1. Question 2, when would there only be 5 dinosaurs left? That would have been after 5 months. All right, question 3 is the hard one. I will be very impressed if anybody got this answer. So to write this function, we always start with y equals, just like the last time. We have our starting value that goes in front as our coefficient, so 160. And it's going to be multiplied by something, by what it's changing by here. Okay, so we are changing by a half each time. We're dividing by 2. So that would go here. That's our rate. Cutting it in half. And that is what is going to have an exponent. So, for example, if I was doing to the 0 power, so if I was doing 0 here and I was trying to figure out my y, I would do 160 times a half to the 0 power. And a half to the 0 power, anything to the 0 power is 1, so that would give us 160. If I was doing 1, I would have 160. A half to the first power is a half, so half of that would be 80. If I was doing 2, I would do 160. 1/2 to the second power would be 1/4, because I would square both the 1 and the 2. And so 1/4 of 160 would have been 40. And that's kind of how I get that table to match my equation. So again, that equation is definitely tougher to come up with. Okay, so if I would graph it, I can't put 0. The first point I could actually put on our graph would have been 410. So right 4, up 10. Then we have 5, 5. And then I have 6, 2.5. And then I had 7, 1.25. Now here's where it doesn't necessarily make 100% sense in this example, is because we're not going to have half of a dinosaur or 1.25 dinosaurs. But there are some things in real life where you could still have those decimals. I kind of just made this one up to be fun. But this is what it looks like. It starts high and it's going in half each time. And if I continue that pattern and I keep cutting it in half, I will never get into the negatives, because it never involves negatives. I just keep cutting it in half and half and half, and it's going to get smaller and smaller and smaller, but it will never really hit 0. I know it looks like my graph hit 0, but it should always be just above that 0 line, and it keeps getting closer and closer and closer and closer, but it will never go below or never even reach 0. Okay, so that's what that graph looks like. And we call this exponential decay. So when the x value is increasing by the same number, so in this case our x's were going up by 1, but our y values were dividing by a constant number. So we were dividing all of these by 2. So this is what we would consider exponential decay. Again, growth is multiplying, decay is dividing. All right, so in class we would have our commercial break at this point, but we're just going to keep going on. So that was kind of the introduction. Now let's get into making sure we 100% understand our objectives. Okay, so I'm going to look at both sides and see what they were changing by. So our x's were going up by 1. Our y's, that went up 14, and then this went up 32. So it's not going up by a constant. It's actually being multiplied each time by 3. So when it's multiplying, that is growth. This is exponential growth. And just as a recap, multiplying is growth, dividing is decay, linear function is adding or subtracting by that constant rate of change. Okay, so let's do the second one. That was going up by 1. These were changing by going up by 6. That would be a linear function. We had a constant rate of change. All right, next one. Our x's were going up by 1. Our y's, we're actually dividing by 3 here. Dividing is exponential decay. Okay, and that covers the second standard that I told you guys about, which says I can recognize the difference between linear and exponential functions. Okay, so we covered that one. Let's go back. I know we already graphed some, but let's go back to this first objective and practice graphing a few more. And you will have to do this on your homework tonight, okay? So Algebra 2, you get a lot more complicated with this. We're going to try to stick to the basics and just introduce it. Okay, so going back to when we would do t-tables to graph linear functions, we always used 5 values unless there was a fraction. Well, since I don't have a fraction, I'm going to stick to those 5 values of -2, -1, 0, 1, and 2. Okay, and I'm going to plug them in for x. So this would be 3 to the -2nd power, which I can't have negative exponents. That's a no-no. I have to move it and lose it. So this would be 1/3 to the 2nd, or we have 1/9. I'm going to keep going here. We have 3 to the -1st, which again can't have a negative exponent. So 1/3 to the 1st, or 1/3. All right, 3 to the 0 power. Anything to the 0 power is 1. 3 to the 1st power, which would just be 3. And then 3 to the 2nd power, which would be 9. So if I graph this at -2, it would be 1/9. That'd be really small. Oops, -2. That'd be 1/9, really, really close to 0, but not 0. -1 would be 1/3. So up 1/3 of the box. 0, 1, 1, 3, 2, 9. And if I would have done 3, it would be 27. So it's skyrocketing. It starts low and it goes high. That would be considered exponential growth. So whenever there is a whole number as our base, that is when it's going to be exponential growth. Okay, so let's do this one over here. We have a fraction this time as our base. This time it's not going to be exponential growth, it's going to be exponential decay. So it should start high and go low. All right, so let's see if that holds true. We're going to still put in the -2, -1, 0, 1, and 2. This time I'm going to start with the positives because it's a little bit easier to see. But if I have 1/3 to the 2nd power, I would square both of them. So square the 1 squared over 3 squared. That would be 1/9. All right, if I did to the 1st power, which would just be 1/3. Anything to the 0 power is 1. Now here's sometimes where people get confused. If I do to the -1st, that means they would both be to the -1st power. So 1 to the -1st and 3 to the -1st. Since they're both negative, they would flip. So it'd be 3/1, which is 3. And same with to the -2nd power. They would both be to the -2nd power, which would flip them both, which would be 3 squared over 1 squared, which is 9. All right, so this one should start high, and we're cutting it by 1/3 each time. It should go low. Oops, didn't mean to erase that. And so it was just that graph reflected over the y-axis there. Okay, and so that hit the last standard that we had, graphing exponential functions. So again, when you graph them, create a t-table and just plug in your different x's to figure out what your y is. All right, that's it for our lesson today. You do have homework tonight. The answers are posted. Again, shoot me a message if you need additional help. All right, hope to see everybody soon. Bye.